Thank you. So I'll start by introducing a distinction between state management and state manipulation. By state manipulation, I mean the pure business logic side of things, defining pure functions that map one state to another. And by state management, I mean more of the physical implementation, the storage, the reactivity systems. The reason I'm drawing that line is that I want to keep more on the state manipulation side of things, meaning that although the example I will give are in React, the concept really applies to backend as well, or to any front-end framework or state management library. So I'll start by situating state machines in a broader context. So I think there's a distinction which is really well captured by the opposition, by the contrast between use state and use reducer. So technically you can use each or in place of the other, but they do capture different intentions. So on the use state side of things, we're updating by values, meaning you have values in, values out. They do have the same typing. From a business logic side of things, what you care about is that every value succession is meaningful. You really just want to get out of the way and delegate stuff to the consuming components. So it gives things like a form-like things, a complex query object. So if you want to further investigate what you can do in that realm, I find the best tool is functional optics. I gave a talk already about this, but now I'm using this to contrast it with the reducer approach. So meaning that instead of sending a value to update, you send an event, or sometimes they call it actions in the realm of Redux. So here we have a nice traffic light. Yeah, last time I gave that talk, it was a few days before Halloween. It shows up. So we have this example of a traffic light. So you have, well, the three well-known states, and you have one event, which is next, which moves to next event. So we really have an asymmetry between the typing of events and the typing of states. What we want to do is to restrict the allowed transition. So you cannot, for example, go directly from green to red. The result of the same event will depend of the current state. So next event, the result will be green if we were in a red state, and it will be yellow if we were in a green state. Yeah, so that's reducer, and it has a well-known typing and property. And state machine is a special case of the whole reducer thing. So in the world of React, like the most well-known ancient way to organize around reducers is Reduct. But there is, like, now in vanilla React, you have use reducer. Use action state is also same thing, but like more on the server state, but it has the typing of a reducer function. Sustant is a more lightweight way of doing thing. In Jota, you have Atom with reducer, and you have less known things such as xState store. It's not the same as xState. It's really a great typing experience. If you want to have like type inference and that works super well to do that kind of workflow. It's my recommendation. You have a two-stand adapter, which called two-stand XS, which does the same thing. And you have my own constellar library. I'll maybe give a few words about it later on. So let's start with the first example. It's very classical example. You'll see it all around, and there's a good reason for it. It illustrates well things. So in the naive way of coding things, you have a loading stuff, and you represent the state by two independent flags. So what's wrong with this? First of all, on the 4 possible combinations, there's one that is illegal. So if you have loading true and error true, that doesn't make sense. And it will trigger down to having a bogus user interface. So you really want to make illegal state irrepresentable. The other problem with using 2 flags is that you don't capture the fact that events do have a succession in time. So the loading flag can only go from true to false, and the error flag can only go from false to true, but it's not captured in those flags. It would be to know that your program is enforcing this, you would have to go and look in your handler. So your state manipulation logic is dispersed here in the declaration of flags and in the handlers. So simple refactoring, we have the nice diagram. It's so loading, and you have an error event, error state, and success, so on. So I made it like very concise, exploiting the fact that in this case you have an overlap between those types. What matters is you have an initial and a final state. So you can now there's no way to have error and loading at the same time. And the succession is expressed fairly clearly, and all the business logic is in one place. It's in that definition of the machine. It's no more in the handlers. Okay, so the idea of one of the main reasons we introduced state machine is to replace multiple flags that don't really combine, and we want to express a succession of idea to regroup the business logic in one place. What's nice about the finite part of finite state machine is that you can go for exhaustivity. You can run through each and every possible case and think about each of those cases in isolation. It also opens to visual communication. Because it's finite, you can draw a diagram. So it's great to communicate with domain experts that are non-developers too. And even amongst developers, we like this. Because like one source of error is a human source of error is not being able to have a clear and common definition of our business logic. So when we're doing state machine, we really think in terms of state first and event next. So it will be a key design principle. I will come back to this. Domain consistency. By this, I mean that by thinking of state first, for example, you have a state where you can accept a payment, and a state where you can access to what you have paid for. It doesn't make sense to accept a payment in the state you have paid for. But we don't have lots of tooling to handle that kind of thing. It's not logical consistency. That we have typings, we all have all that. But for like a more like business domain consistencies, tools are fewer, and that's why modeling in state machine is interesting. So, but finite state machines have one big drawback, is that they cannot hold data. Like, it's having like just like red, green, blue as a state is kind of limited. So we'll see what we can do with this. So here is another example of a finite state machine. It's a Turnstile Gate. So now it's in the state of lock, and I pay, and it's in a state of unlock. Extraordinary. We're doing great things this morning. So we have the diagram in case you don't understand how that turnstile is working. Very helpful. So here is the implementation. So I've defined the two states and the two events. And so it's important, you have to define the initial state and the transition function. Basically, a state machine is that. It's initial and transition. And I've implemented with the most boring basic things, which is to switch statements. So the outer switch is over the state, and the inner switch is over the event state. Notice that there's a default case on the events. The reason is extensibility. We want to be able to add new kinds of events without having to refactor. But there's no default case on the state switch statement because we want exhaustivity. We don't want to forget to handle one state. Like, because we typed it in this way, that the function must return a state. If I forget to handle a state, TypeScript will tell me, which is really nice. So, and here is a small hook to implement this. So I'm basically passing what I've just defined inside a use reducer hook. We're using like vanilla React. And then I'm binding one handler with just applying this send function, giving it pay argument, and giving it push argument. But nicer thing is, like, you see that the buttons are disabled when it's not relevant. So the way I'm doing this is because the reducer function is a pure function, I can reuse it, and I dry run it. So I take the current state, I send a pay event, but I don't send it to the hook. I just like pass it to the function and check whether the state is the same or not. So the reason why I think is interesting is that there is no knowledge of my business logic here. So I could say, like, if it's in a paste, if it's in a push state, it cannot be. Now the business logic would be leaking outside. So having that pure function and dry running it keeps that benefit of having the state, the business logic in one place. And yeah.
So I noticed maybe you said this, that you're using the event-based reducer system instead of the state-based.
Yeah.
So that basically works best with finite state machines, is to use events.
Event is part of the concept of a finite state machine. Yeah, but I mean, what's an event? An event is just that you have some kind of state with an updater function, and if the types are different, I call it an event. If the types are the same, I call it a state. So, like, you could implement it any way you want. It's not, you don't have to have the word event in the documentation of whatever star is handling it.
You say zero knowledge of the state.
Yeah. Oh yeah. Yeah, you know, you need to know the typing of the state machine. but of course, like it's not floating in space, but beyond the typing, thanks for the precision. You don't need to know which events will lead to which states and which state transition are possible or not. That's, zero, it might be an overstatement. Minimal knowledge. So here is just the component. So because all the logic has already been defined, it's fairly trivial. We're calling what we had defined in the hook. Okay. Now I'll introduce what I've stated earlier we'll extend the capacity of a state machine to hold some kind of data or payload. So the most well-known strategy to do this is exemplified by xState context. So the idea is that the machine has a special variable called context that is always shared between states, and you put information there. It's proven to work. So many people have used it. There's no way to say it's bad, but I feel there are shortcomings. You get back to that situation where some illegal states are representable because some data are relevant really in a few of the possible state types, and we're leaving some money on the table. We can do more with typing to help us thinking. So the approach that I want to exemplify, I call it multiple states because I haven't seen it much, so there's no official name. So you have the state types like that we have seen, like the qualitative part of it, and a state payload. And the point is that they are coupled, meaning that a certain state type means a certain typing of the payload. So I'll give concrete example of this. So we'll extend that. Oh no, we'll have a timer, like such a great application. So as you see, and we can reset. So as you see, there's a type stopped and a type running, and the payload is different. So when it's stopped, we have just the amount of microsecond that has been elapsed. And when it's running, we have a reference point in time, and we subtract the current time from that reference point to know how many seconds has been elapsed. Both are number, but they have a fairly different semantics. So I think it's much clearer to implement them with different payload, with different typing, different names. So here we have our diagram. So we have a stop and running, and we have the toggle event, which goes from one to the other. And we also have the reset event that does a self transition. So it moves from stop to stop and from running to running. So just in case you don't understand what is a reset, that's putting it back to 0. And so the way I'm doing it is we have this two state as I've explained earlier, and we have the event. I'm passing the current time inside the event. Like we could have a non-pure function that reads the time, but I find that doing this makes stuff more testable. In your test, you can provide a number. I like that. So, and here we have like once again the initial state. It's stopped and no time has passed, and we still have this nested switch statement with stop and running, and like functions where our events handler. So nothing more to see. That's the point. But now we need some kind of getter. So the time that we're displaying we won't calculate it the same way depending on our state. So it's a getter function with the state. So when it stops, we just return the simple elapsed value. And when it's running, we take the current time and take the difference. So ideally, that would be collocated with the states. Like we would define, let's say for the stop state type, we would define the two transitions and this getter all be in this idea of taking of one state at a time. So if you use a library, it's one benefit you will get. You will be able to collocate this, but like if we're keeping things simple, we have to accept that small inconvenience. And here again, we're defining a hook with that state machine. So once again, we're passing this definition to a use reducer hook. And the other thing is what I'm displaying on that button. So when I click stop, it goes to the stop state. And when I click run, it goes to the running state. So once again, I want to have zero knowledge of the state machine. So I'll do a very similar strategy. So I'll use my reducer function and pass it the event and look at the resulting type. So and I'll have a little handling. So if the next state is a stop state, I'll display stop, and if the next state is running, I'll display run. So and again, the final component is just like plugging stuff in. Okay, but now, yes, sure.
Go back to a couple of slides.
Yeah.
Maybe one. How would this be different, let's say?
It wouldn't, like, it's a pattern. So it's a pattern you can apply everywhere that it's. It, okay, but well, Redux, as the name says it, offer you a reducer. But what it doesn't offer you out of the box, but yeah, that you still can implement, is this idea of thinking in different states or state types. That's not in Redux per se. Where was I? Yeah. So one thing we all have experienced this with the turnstile, that you pay and you think you've paid, you push the gate and you get hurt. So that's not a nice user interaction. So we want some kind of feedback whether this payment has passed or not, because we're nice people. I am, at least. You do you. So if we use, like, yeah, I didn't introduce if. Ooh, there's a slide missing. Okay, I'll do two things at the same time. So yeah, so you pay, and then you wait and see whether the payment has passed or not, and then you get in a success or an error state. Yeah, little technical error here, sorry. So have I inverted the slides? No, I just went too fast. No. Okay, sorry, I'm recalculating what I need to do here. Okay, so you pay. Then you have to wait a little bit to see to see whether the payment has passed. So you are in a payment state. And so we'll implement an effect and that will like basically trigger that like post request to try to handle the payment. And then it will succeed or fail. And if it succeeds, you will get to an unlocked state. And if it failed, you'll get to an error state and get back to lock. So that payment state is useful. Like you want to display on the Turnstile Gate, we are now paying. But those success and error state are junk state. By this, I mean that all we want to do is send a message upwards. So we don't really want that. So to avoid creating jump state, we will need to give another capacity to the state machines, which is to send messages. So for the payment, we will just, that's the slide I forgot, we will do it. We will just implement this as a good old use effect hooks that react to a payment state. But then for the return, for the notification of whether the payment has passed or not, we will give a special capacity to send messages. So effects will be for two-way communication between the machine and an external system, and messages will be for one-way communication from the machine upward. So we have the states, so locked, payment, and unlocked, and we have different events, so pay, success, error, and push. So notice that pay and push are events that are triggered by the user, and success and error are events that are triggered by the system. Yes? It's, yeah, no, so payment is a true state, meaning that it's meaningful in the interface. Like you want to, what's consuming your state, like for here, for example, the UI framework, wants to know that we're in that payment state and display, please, where we are now paying. But the success state, we don't want to display we are currently in the success state. We just want to send a notification. It doesn't add nothing meaningful to the UI. It's just something annoying that you want to get rid of. So,
and like if you have a success, you can still have like a processing state. You know, like when you have like in your case it's a form, it's like it's processing.
Yeah.
You can have in between, so it's not a junk state. You can still use that thing as like as processing.
Bear with me.
No, but like when you have like a form and then you have like the state,
Yeah.
You can have something in between. There's like still a junk state.
Okay, yeah, bear with me. Like the payment is not a junk state. It's a junk state in the concept that I don't want to and I have something better too. But like of course, it's always specific to your application. So so because we want to give the ability to send messages, we cannot use the use reducer state anymore. We have to have a special use machine hook that just takes so the state, the event, and a third component, which is because we will inject the capacity to send messages. We don't. So the reducer here is on the success event, it's emitting a message and returning directly to the unlock state. You don't have that way we avoid to have a controversial junk state. And so, yeah, here it is. And yeah, demonstration. So we're waiting and payment refused, no luck. Let's try again. Yeah, I got it. So the point is, you see, when both are disabled, we're in in a payment state. So that's meaningful. I want to display this to my user. But as for the notification, I don't have to hold my UI in a notification state. I can just send a notification. But of course, it's a matter of design. If I wanted a UI where something, if I wanted to have, like, let's say, a dialogue and you click yes, I have seen it, then it would be a full-fledged state. It wouldn't be a junk state anymore. So and I have a use effect. So when we're in the payment state, I send I use a payment handler, and and the handler has the ability to send back an event to the machine. So yeah, here we have the event listener that just use a toast component. It really sends an event upward. State explosion. So as the complexity of your state machine grows, you will face, like, the same clean code concern. Like, instead of having a God class or a God object or a God function, you have a God machine, meaning that you're dealing with multiple responsibilities with different abstract level in the same machine. Or you can also, just if you think of the amount of independent state of a complex application, it gets basically impossible to handle. So as usual, we'll need way to have simple state machines that's combined. And so there's really two big strategy to handle complexity with state machine, which I call connect and compose. So connect is that you have simple state machine and you have something else that makes the binding between these. So it can be as simple as your React framework. You have two state machines, and you don't have to have a big state machine to handle both of those. You can messages of one state machine can correspond to events of another state machine. So it's the most basic way to get away with complex state machines. The other approach is more algebraic. It's about composing state machines, meaning you have some operations that takes simple state machine in and get a more complex state machine out. You have a complex algebra about these. So most obvious thing is a product state machine, which is akin to Redux type pattern. You can have hierarchical state machine. By this, I mean that you have a machine that is active when your main machine is on a simple on a state. So you have a substate, and some machine is that, like, your higher state selects which one of the many machines are active, and history machine is that when you switch to which machine is active, like, the system remember the last state and can come back to it. So this was developed mostly in a context way before React, 1987. It was for an embedded system, actually. There's an article where they're analyzing an 80s watch with all those modes, and they're very detailed about how it works. The point is, when it was thought of, you wanted some kind of visual communication, and, like, the state machine was the main entry point of your application. But, like, often we don't need this because we have another entry point, so such as a framework. So use cases are so component logics. There's a Zag component framework. So it's a component that are that works in many frameworks. You have Vue, you have React. So they do abstract logic of their multi-framework component into a state machine, and they consume the state machine differently in each and every framework. So it's used a lot in embedded system. And so using a library versus a pattern. So a pattern, like I did here, you don't have a learning curve, fewer dependency, but sometimes less descriptive, like you have switch statement instead of having a simple objects. So most well-known library is xState. It has super good dev tools where you can visualize stuff. Some features are really geared toward having visualization. So my issues with xState is the contexting, as I've explained earlier, and the fact that it has its own reactive system that you then have to bridge with React or Juliette or so. So having like a pure function to me is simple, but you always have binding with xState. So Robot is a lightweight library, less known. It's very basic state machine implementation. I have my personal implementation of optics and state machines. So my two selling point, if you will, is that to start with pure function, although I have I can do interesting thing in Juliette integration, and that contexting to have instead coupled payload states. And yeah, that's about it. So here is my LinkedIn profile, and here is the QR for evaluation. And by the way, I'm looking for a full-time position if you think I'm smart, or you can give me a review on LinkedIn. That would be really appreciated. Thank you.